Here's another problem that we can use the work and energy principle to solve. Involves a plunger and a ball on a track, just like a pinball machine. We have a ball that's located just in front of this plunger to begin with, and we're going to pull back the plunger a distance s. I've highlighted this where we have our initial position right here, and our displacement is pointing positive towards the left like so. So we have to pull back on that plunger to load up this ball and then spring it up onto the ramp itself. So the question says that consider a 0.5 kilogram ball of negligible size. It's fired up a vertical track of radius 1.5 meters using a spring plunger with a spring constant of 500 newtons per meter. Plunger keeps the spring compressed 0.08 meters when S is equal to 0. So what it means is that even before we've even pulled back on the plunger, right at this vertical line, that I'll do it again in black, okay, the spring is already compressed. It's pre-compressed by 0.08 meters at that point. But we're going to further compress it by pulling it back further, creating potential energy stored within the spring, as we've learned about in our class, and then allow the spring to do that work, transfer it, that work, that energy to the ball, and allow the ball to fly up the track itself. So what we're looking to find here is the distance s that we need to pull back on that plunger so that the ball will begin to leave the track at theta is equal to 135 degrees. So again, let's start by writing down what is given in this problem. We know the mass of the ball is 0.5 kilograms. We know that the radius of curvature is 1.5 meters for the track itself. We know the spring constant is 500 newtons per meter. And we know that when the plunger hasn't even been pulled back at all, when S is equal to 0, we know that the spring is compressed by 0.08 meters. Okay. What is it that we're trying to find? Well, we want to know how far we have to pull that plunger back. So what's that distance S required so ball will leave the track at an angle of 135 degrees. Okay, 135 degrees, where the angle theta is with respect to this vertical, as we see here. Okay? So a pretty interesting problem. And I said that this is a great problem to solve using work and energy principle because, again, this is a problem that involves speeds, magnitude of velocity, distances, and forces, as we're going to find out. When we see this, we recognize that this is a great problem to solve using our work and energy principle. If we were to try and use the equation of motion, we could potentially do so, but we'd have to solve for accelerations and then convert those accelerations into velocity. That adds another step. So why even do that? All right, well, let's draw the free body diagram for this ball when it's loaded up into the plunger. Okay, when it's loaded up into the plunger at this initial location, there's going to be a force F called the spring force that's pointing to the right. It's going to, we're compressing the spring's going to want to return to its equilibrium position, so in order to do so, it's going to push the ball to the right. It feels a normal force upwards, and it feels a weight force downwards. And the reason why I'm not drawing a force to the left in this case is because we're assuming that we've let go of the plunger. So if we're pulling back on the plunger, of course, there'd be a force pointing to the left to account for that, but we want to consider when we've release the plunger and the ball starts accelerating, moving to the right. So we have a net force towards the right, which causes acceleration in that direction. If we draw a new free body diagram, when the ball has reached an angle of 135 degrees, if I were to draw it up there and then get rid of that little line that got tagged along there, if we were to consider the ball at that location, the free body diagram there, well, we would still have, I don't know why this is acting up, but we would still have that force of the weight pointing directly downwards, okay? And we would also potentially have a normal force from the ramp itself. Now the question asks us to determine how far we have to pull that plunger back such that the ball will leave the track at that angle of 135 degrees. So if this is an angle of 135 degrees, the ball will be leaving the track if we do this properly, meaning there is no normal force at that point. The normal force will have dropped off to zero, and the only force we will consider is the weight force. Okay. So I said that this is a great problem to solve using the work and energy principle. The work and energy principle says that the change in kinetic energy comes about from work that's put into your system or work that's taken out of your system. Or another way is saying that your initial kinetic energy plus the amount of work that's put into your system from your initial state to a final state is equal to your final kinetic energy. Okay, you need to put a net amount of work into an object to change its kinetic energy. It's another way to state the work and energy principle. So the amount of work that's done in this scenario, well, there's two forces that we need to consider. First of all, this first stage where the ball is being pushed by the spring, that spring is doing work on the ball itself. Later on, the weight force does work on the ball too because it goes up on the ramp, and so the weight force is pointing downwards and the displacement as it moves up the ramp is upwards in a general sense. So there's negative work done by the weight force itself. So if we were to consider each one of these forces, well, let's look at the normal force. We kind of glossed over that. The normal force is pointing upwards. And if we were to consider any other intermediate state on the ramp, we would notice that the normal force is pointing perpendicular to the direction of the object's motion. The normal force does no work. It's always perpendicular to the direction of motion. Work, after all, is the product of your force magnitude times your distance magnitude times cosine of theta. And if the force that you're considering is 90 degrees or perpendicular with respect to the direction of the object's motion, then that force does no work. The normal force is always perpendicular to the direction of the object's motion, so it never does any work. The work done by a spring, we've written this down, is negative 1/2 k s2 squared minus s1 squared. These s values, S2 and S1, indicate elongations or compressions of the spring. It doesn't indicate the length of the spring at any moment. It just says by how much have you compressed the spring, how much have you elongated the spring. This negative sign, I like to think of it as just a simple reminder. The work done by a spring can be negative if the force is in the opposite direction of the object's motion. Okay, now this is where it gets a little bit tricky here. So if we plug in for our kinetic energy for position 1, well, this is easy. 1/2 mv1 squared plus the net amount of work done from some initial state to some final state. Well, let's call our first state at the release point. When we've pulled back the plunger and now we've released it. So that first location that we're considering is at the release point, right when we release the plunger. The second point, that's going to be at detachment from ramp. Okay, so our initial position is when we've pulled back the plunger and we release it. That initial instant, that's our first position. Our second position is where the ball leaves the ramp. Okay, so our first position says that your initial kinetic energy plus the amount of work that's done from state 1 to state 2 is equal to your final kinetic energy. We said that there's two components of work. We didn't actually write down how much work was done by the weight force. The work done by the weight force is just going to be equal to the negative W delta Y. Work done by a weight is negative W delta Y, where if delta Y is a positive value, the object's height or altitude increases, the work done by the weight would be a negative value. So this would be equal to negative weight times, if we were to call our datum at its initial position, then the height at its final position will be, well, the radius, 1.5 meters, plus 1.5 sine of 45 degrees. Where did I get this number from? All right, well, we recognize that the object is going to go on a ramp that looks like this. We're interested in knowing a location that's equal to 135 degrees based off of the geometry provided in the problem. We know that the radius of curvature is 1.5 meters, so this first distance is 1.5 meters. But we need to also account for the distance I'm drawing in red here, which is going to be added on to that 1.5 meters. So its final height, h final if you want, is going to be 1.5 meters plus 1.5 meters sine of 45 degrees, where 45 degrees is this angle right here. The radius of curvature remains the same, 1.5 meters. Sine of 45 degrees will give us that length that's in red. Okay, so the work done by the weight is negative weight times delta y. So negative weight times delta y is 1.5 meters plus 1.5 meters sine 45 degrees. Okay, we need to insert this into our work and energy principle. So we have, as I started on the last page, 1/2 mv1 squared. And it's not plus. We have minus 1/2 k s2 squared minus s1 squared minus w delta y we just wrote out the last slide, is equal to 1/2 mv2 squared. Interesting. Okay, we know that we're starting from rest, so the initial kinetic energy is 0. S1, this is what we're looking for. This is the problem statement. The problem is looking for S1. We know what S2 is because that's going to be the compression that's given for us. That's 0.08 meters. When we let go of the plunger is going to push the ball forward, and the spring is going to return to that initial compression of 0.08 meters that exists when no force is applied to the plunger itself. So that S2 value is 0.08 meters. We know that. We know the K value that was provided for us. We can determine the weight of the ball from mass times the acceleration due to gravity. We know delta y. We solved that. We know what the mass is. Uh-oh. We don't know what the speed of the ball is when it leaves the track. It's not 0. It's still going to be traveling with some speed. That's a non-zero speed. How do we determine that? Well, if we think again about this ball as it's going around the track, finds itself at this location, we could draw a free body diagram for the ball over here. As we've done already, we have the weight force pointing downwards. There's no normal force because at this instant it should be leaving the track, so there's no normal force. But this is a great problem to solve using our normal and tangential direction. Normal towards the center of the curve, or tangential direction is in the direction of its motion at that given time. This turns out to be a 45-degree angle. Why are we using this equation? We're using this equation because we know that the sum of forces in the normal direction is equal to the mass times v squared over rho. Meaning, the weight cosine 45 degrees is equal to the mass v squared over rho. We know the weight, we know the mass, we know the radius of curvature. The only unknown in this equation is the speed, which we can solve for. Notice that this also becomes mg cosine 45 degrees is equal to v squared over rho, the m's cancel out, so the mass doesn't actually factor in this portion of the problem. But plugging in the appropriate values for g, 9.81 meters per second squared. For rho, this would be 1.5 meters, and so forth. We find that the speed at that location when it leaves the track is 3.226 meters per second. Now we have enough information to solve this equation that I'm going to be circling in blue, our work and energy principle. We've determined what V2 is, the speed of the ball as it leaves the track. So all we need to solve for now is that S1 value. So plugging in, we would get negative 1/2, 500 newtons per meter, that's the spring constant, times 0.08 meters squared minus S1 squared minus 0.5 kilograms times 9.81 meters per second squared. This is the weight times the height. Turns out to be 2.56 meters. This value comes from the equation that we wrote down here. Okay, 1 point, or more specifically, in green, this portion right there. If you punch that into your calculator, you'll find that that's equal to the value I just plugged in there, 2.56 meters. And this is equal to 1/2 times the mass, 0.5 kilograms, times its speed, 3.226 meters per second squared. We have one unknown. This turns out to be S1 is equal to 0.179 meters. You need to pull this plunger back 0.179 meters in order for the ball to start to detach from the track at an angle of 135 degrees.